It's my great pleasure to introduce Professor Naser through the Thar Talk series. Professor Naser had done his BS and MS in civil engineering from the American University of Sharjah, following which he had done his PhD in the area of structural fire engineering from the Michigan State University. Currently, he is serving as an assistant professor at the Glenn Civil Engineering Department at the Clemson University and also as a member of AI Research Institute for Science and Engineering. His research interests cover the areas of causal and explainable artificial intelligence and machine learning, structural fire engineering, and understanding the overall behavior of materials and structures susceptible to extreme environments. He has co-authored over 70 journal articles, 20 conference papers, and one textbook. He is currently serving several committees. The notable mentions include ASC Committee on Advances in Information Technology and Fire Protection, ACI Committees number 133, 216, and 440, as well as PCI Fire Committee. Today, Professor Naser will be delivering an expert talk on hiding in plain sight, the role of machine learning in modernizing civil engineering, a very topical theme in the modern civil engineering context. Thank you, Professor Naser, for accepting our invitation to share your insights to all of us through the Thar Talk series organized by the AID School. With this, I invite Professor Naser to deliver his expert talk. Over to you, Professor Naser.
Very much, Dr. Ravi. Thank you to the IIT panelists as well as leadership for inviting me for this talk. I'm very much humbled and in your debt. Today's talk, as Dr. Ravi mentioned, it's titled Hiding in Plain Sight. So basically, it's all about the role of machine learning and how can we use it as civil engineers in our domain. This talk is derived to be in a way that showcases some of the successful case studies that we have done with AI, as well as towards the later part, we're trying to ask some questions that could be a little bit interesting to us as engineers because we don't really design algorithms, we're more likely to apply them. And hence there is a fine line between our intuition of how algorithms work, as well as if they really work in our favor, or is it just going to be like data in, data out. So to start this presentation, because I know there's going to be a lot of civil engineers with us, to start with, AI basically is, if you would like to think about it from a big picture point of view, it's a computational technique, and all what we do is we collect data, we apply these techniques, and we are trying to figure out some hidden patterns within this data. And when we do that, we are aiming to see, okay, will these hidden patterns of the things that we haven't seen before can help us figure out maybe prediction of phenomena that would help us later on in our careers. In our case, we're talking about civil engineers. And, you know, civil engineering is not it's not really a flexible field. We tend to have some inertia and resistance toward the new tools. But the good thing is about AI, it's been very, very well used in different fields, material sciences, robotics, medicine, even social sciences. So whenever we as civil engineers try to get to learn to AI, it's always good to start from the very, very basic fundamentals to see the big picture. And then from there, we would go to learn a little bit more about those details. If you can see at the bottom right-hand side of my picture, you can see Teslas. Teslas are a prime example of how we can use AI to come up with something that used to be traditional driving cars, and now it basically the cars that drive us around, which is very, very cool, very interesting. If we can take the same principles and try to apply them to civil engineering, that would make our life much, much easier, which we will see herein. Now, the other thing is to think whenever we think about AI, we always try to see, okay, how does this AI help the industry? If you look at this figure here, you would see this goes back to 1950s all the way to 2010. It's a survey done by these researchers at Fort Kelms, and it shows that when we started to use automation in general, you can see that there is a positive trend upward, which means that there is good stuff happening to our fields. For instance, agriculture is significantly rising, almost 16 times improvement just because of automation. Manufacturing, wholesale and retail, mining, overall economy. And if you look at construction, you can see that construction is almost steady. So we didn't really leverage automation that much. Nowadays, we're starting to see automation. And the goal is perhaps AI can help us emphasize the importance of automation, maybe make this our field, our future, go risingly. in the above. So this is from an economy point of view. If you would like to think about, research and academia point of view, you would see that there is a lot of, publications in AI in general. Started, late 80s, mid 80s. Whenever there is publication, there's a very good trend for patents because now people can figure out we have software, we can patent them, we can make money out of them. But this is in computer science. And as you can see, the number of publications is significantly high per year, more than 100,000, 150,000 papers almost. If you go back and look at our field, civil engineering or structural engineering, you would see that the numbers are also rising successfully, but the numbers of publications is minute, is very, very small. It's almost like maybe 1,500 papers a year as compared to 150,000 papers in computer sciences. If you go back to my specialty in structural fire engineering, you can see the numbers are very, very small. So this tells us that not only civil engineering is a little bit lacking, but also sub-disciplines of civil engineering are also lacking. So this brings up a good question. Well, why are these publications now and attempts are being taken care, going risingly up? And how can we make this, how can we use it to help us understand and better perform our duties and our jobs? So if you bring everything back to the fundamentals, you would see the following. We have evaluation methods. We're engineers, we're scientists. What we do is we design experiments, as you can see here. And what we do is we observe. We try to see responses. Once we see different responses, we have a baseline. So this baseline can tell us if this happens, then you're most likely to see this. We take all of that, and now we try to evaluate performance of structural members, of components, of materials under similar conditions or a little bit different. We try to predict, and our goal is to come up with a tool that we can predict with, for instance, finite element simulation or finite element analysis always help us to predict different phenomena that we usually use in civil engineering without having to rely that much on experiments because they're expensive, they're costly, you have to have a lot of time, and most importantly, it's very, very hard to test every single parameter. So you have to be a little bit, creative of what parameters to control, to carry out, and then come up with tools. And the goal is to make our life easy. We can't be testing every single element we're going to be building in a building, but if we have a tool, it would make our life much, much faster. It will make our quality of life also reliable. So this is the big picture. Now, if you would like to think a little bit of a more complex experiments, what we do is fire tests. As you know, we have fire furnaces, massive structures. Or what we do, and then we have specimens, we put them, we turn the fire on, and then we do tests, and we measure temperatures, we measure deformations, we try to see the failure modes, how does the temperature affect the material at the material level, as well as take that and apply it to the member level, and hopefully potentially on the elemental and structural level. So it's a very, very lengthy process, and we can do this with experiments. We can also do this with simulation, as you know. And if you would like to break things down, you would see that the process is lengthy because the phenomenon associated with the problem is complex. It's not easy. If it was a simple process, then the design or analysis would be a simple procedure. Once the phenomena become complex, then you have to have too many steps to come up with a proper design or analysis. And this now brings in a good concept. Well, I know if the phenomena is complex, I have to carry out a complex analysis, but is there a way to simplify it? In a way, simulation, FE simulation, simplified experimentation. Can we do a similar thing using a different tool, perhaps maybe AI? So it's a good point to pause and think. Now we have traditional method or classical method test simulation. If you would like to do tests, whether it's fire tests, concrete tests, steel tests, material tests, you're likely to have some kind of limitations. We're not going to be able to see, for instance, certain behaviors we have to control. We don't have many different specimens. When it comes to simulation, the basic thing that always comes to mind is we don't really have a standard way to apply simulation. Basically, simulation becomes more of an expert opinion. You use different parameters, inputs, you use different solution algorithms to come up with to solve the problem on hand. But your design or your model, for instance, in this case, a partial collapse, might be a little bit different than the one that somebody else would do just because they use different input parameters. And this now brings in a question of which parameters do we have to use, which material model we have to use? Are we confined with the software itself? Can we use other things? So all these questions now shows you the pros and cons of different evaluation methods, and makes you think, well, maybe there's if all these things are taken for granted, because everybody has been doing them for so long, perhaps we can do a little bit, some improvement. And the improvement is, at least when I think of this problem, is going to be AI, because we know that if you think of an engineering problem or a civil engineering problem more specifically, we know that we have a large number of variables. We know that each variable is highly variable. There is a lot of uncertainty. And the relationship between the variables also has, it could be linear, nonlinear, interlinear, independent. There is a lot of different relationships. So all these complications, we usually simplify in our analyses and experiments. We assume them that they're there, but we go with it. But perhaps there is a way that we could use AI to be our ally in this problem. Because now, if you remember AI, you remember big data. Big data means you have a lot of observations. Perhaps some of these observations can help fill in the gaps of those items that we can't really, perhaps measure or quantify very, very finely. So simply put, whenever we talk about AI, some of the questions I usually see from students is, what's an algorithm, what's an ensemble, what's a surrogate? And all these are definitions, and without knowing the definitions, it's going to be really hard for us to go beyond the realm of this presentation. So the way I would like to simplify it is, think of an algorithm as a process, and a process has a certain rules. For instance, this algorithm, a process, looks at the data, does some analysis, gives you an output. If you combine several algorithms together, you're going to have an ensemble. So an ensemble is a group of algorithms. If you hear, for instance, now in publications, you would see surrogates. Surrogates are a simple model or a simple algorithm that can simplify a more complex algorithm or a more complex model. We also think about fitness metrics. Once you have these algorithms and you see numbers and outputs, how do you make sure that this algorithm is working properly? So this is why you have to go back and analyze its fitness, see if it works in a way that's comfortable to you. You can see that, for instance, you have R squared of 95%, R of 98%, and so on. And the big picture under AI or machine learning then becomes, we have all these tools. We have supervised learning, unsupervised learning, we have reinforcement learning, we have semi-supervised learning. And you can even go beyond that a little bit too. So the question becomes for civil engineers, well, which one can I use for my problem? Am I going to be using classification, regression, clustering, association, rule of thumb, all those things? So it becomes just too much information for us. And because we don't really teach AI in a civil engineering curriculum per se, it's like, this is too much, perhaps it's not the right time to do AI. But the thing is, I'm trying to emphasize here is, we don't really have to learn everything at once. You take it as baby steps. You start with something, you start with a component, and then you go from, later on. The good thing about this time and age now is we have many of these algorithms already developed for us by our colleagues in computer sciences. They develop algorithms, we apply them. So we don't really have to code them per se. If you could code them, that'd be great, because we could develop something for our own. This perhaps could be in the very, very near future. But at least for now, these algorithm neural networks, different techniques are already done. So all what we have really to know is learn how they work, why they work, apply it to our problem, and see if we can learn something good or positive from them. And we have, as I mentioned, different techniques and stuff, and it could be complex, but the thing I'm trying to emphasize is always start with a simple idea and then go beyond from there. This is how your life becomes a little bit easy. So now I'm gonna bring an example. If you think of one of the simplest structural elements in a building would be a column. You have a column. Columns carry applied load. So basically, you have maybe an applied load here. Maybe you have another story that moving the load. If you take this column and apply some temperature to it, what's going to happen is you're going to start to see the rise in temperature. So basically, temperature in those steel rebars or within the column itself will start to rise, slowly. Then go on. This is the temperature here in orange. This is the temperature within the element. And if you start to look at this if you take a step back and see, okay, well, although these members here, they have similar geometry, similar material properties, but the temperature rise is not similar. You can see there is a very large gap, almost 600 degrees, 700 degrees to 200 degrees within the same element. So this shows you something very interesting. It shows you that although we're testing similar members, plus or minus some deviations, the output we see, the observations we observe are significantly large. And now this brings up a question. This would say, okay, why are we seeing this? Well, because maybe the geometry is a big, small, maybe the material is conductive, insulated, maybe we have insulation, maybe we have dense concrete, maybe we have different boundary conditions, different applied loads, all these things becomes a problem. But the thing that you would see, the most important thing is if you look at this figure is the following. If you apply temperature to a column, regardless of its features, you'll always have rising temperature, which makes a lot of sense. If you heat something, its temperature will rise. And this will always be true. And if this is true, then perhaps there is a way for us that we can link or tie the temperature effect to all these factors with the output we have, because this is what experiments do. You test this, you get a point, 1 point, and then you test another one, you get another point, and then you collect points and you have a best fit empirical equation, for instance. You can do the same thing with a FE simulation. You run a parametric study, many simulations, and then you have curves like this, and then you would say, okay, well, the influence of this parameter on this behavior is so and so. And instead of doing all this cycle, perhaps if I can teach an algorithm this phenomena here, maybe I can come up with a very easy solution. So the problem will not be very complex. I won't have to spend much money on experiment. I won't have to spend too much resources on different simulation, because it costs energy. You have to have software license, you have to train students to apply it, you have to have different expertise. So let's think of it from a much even simpler problem. Let's think of beams, because beams are easier to visualize. If you have a beam, you apply some load, you apply some fire, temperature will rise in the beam, always be true. And the same thing, the beams will start to degrade. The material will start to break down because of the heat effects. Now, regardless of the amount of loads, material will always degrade because the material is linked or is tied to the effect of temperature. Once you applied loads, if you have here higher load than here, then the deformation you will see, remember deformation you will see in this beam, in beam one will be higher than the deformation you would see from a beam that's slightly loaded, although they both have the same temperature, although the degradation is the same. So now this brings up a very cool idea of, okay, if the behavior I'm interested in from a civil engineering point of view, which is deflection, because if a beam deflects too much, we're going to have collapse, can be captured easily by this, then I should be able to tie all these features together. And the way I'm going to tie them together will make it much easier for me, because now instead of doing a test or an experiment or a simulation, I can use AI to give me the answer right away. I don't have to do the test and then wait for the test and then measure from the test and then say, okay, this is 1 point only. I can teach AI the physics behind the phenomenon and then take it. And then now I have a tool that can link everything together very smoothly, very fast, as I will show you in a little bit. Now, what are the features we're talking about? Well, think of it from a physics point of view. Well, you have a beam. If you have a beam, you have geometry. If you have geometry, you're going to have material filling this geometry. If you have material, geometry, and a beam, then you have to have loading, because we have the beam to resist loading. If you have a beam, then you have to have boundary conditions to support the beam. If you have boundary conditions, then you're going to have the effect of fire. All these things interact together to give you a phenomenon. So this is where we discuss something like mapping function, for instance. This is a concept. A mapping function says, okay, when we do tests, we come up with empirical points, we best fit them. This is like an empirical equation. That's also a mapping function. It maps the inputs we have to the output that we see. We can use the same thing with AI. We can use the same thing with statistics. We can do the same thing by asking an expert. Like, for instance, in this panel, you would go to a professor and say, Professor, what do you think if I do this to the beam? What do you think is going to happen? Because the professor knows the physics of the problem, has seen many cases before, they can give you a nice example or a nice answer to your problem. Expert opinion. Now the goal is, can I teach AI to be an expert in this phenomenon? I have a member, beam, column, have AI, a mapping function. I will be able to find the performance very easily. So if you can find this mapping function or algorithm, you can do things instantaneously. You don't have to do FE simulation for 8 hours or like 4 or 5 days to run. It's instant. So you're reducing your time significantly. And if you think about the industry, time is money. That is a lot of time, a lot of money being saved, which means a good bonus at the end of the year towards you, hopefully. This would also say, okay, now if I have this and I have AI, maybe I can change the landscape of civil engineering, not just civil engineering, perhaps every engineering, R&D, the way we do R&D, we don't have to do tests. We don't have, or we don't have to do tests that much. We don't have to do simulation that much. We just need a few times to come up with some data. And the good thing is about our literature is it's full of data. There is a lot of data going on there. So the way to think about AI is you have to have a model. Basically, you have to train the model, or develop a model. And just like FE simulation, you build the geometry, you mesh it with elements, you apply inputs, material properties, boundary conditions, you run it. Same thing when it comes with AI, except we collect observations, data. Remember, AI, big data, or small data. We need to have data. We choose an algorithm. We apply the algorithm, and remember, I'm saying we apply because we, most of the time we don't really develop algorithm. We still apply at this stage. Algorithm will give you an output. You would evaluate the fitness of the algorithm. If it's fit enough, you would say, okay, this is good analysis, this is good training and validation and testing. If not, you would start to do like retrain the model perhaps, or maybe if everything is fine, then you would start to use the model to predict future events or future incidents. And of course, with AI, there's going to always be issues with overfitting, biasness, different stuff. So it's good practice to keep an eye on your AI model just to see how it behaves over time. So for instance, in this case, now I'm trying to move away from AI a little bit more into case studies that we have done so far, we have seen. So the simplest thing about an AI algorithm is basically a neural network, because they have been for so long with us. We know how to design and how to apply them, and they're helpful. They're very generalizable, and they're easy to apply. They don't take that much time to develop. So as you know, a neural network has a series of layers. You have an input layer. This is where your input is. So this is basically going to be like an FE simulation. You would build the geometry, apply the material, apply the inputs, boundary conditions, meshing, all those things. You have hidden layers that do this computational analysis of those data points. And then you have an output layer that gives you the prediction. This is the algorithm very, very simply. Now, the thing is, if you think of this structure here, we don't know what's going on. To us engineers, we think of equations. We want to see a function, or let's say f prime c equals square root of so and so and so and so, or moment equals 0.85 f prime cb over as fy, all those things together. We need to see parameters. We need to see the relationship between the parameters. Without that, we're always worried. We're always like hesitant. Well, I don't know how this is working, so it's scary to use because I can see it. We've spent so many years in industry and in academia, as well as in undergrad, grad school, learning equations, how to design equations. If you see something like this, it's a black box, and this is the intuition here. It's a black box. We don't really know how it works. Some computer scientists don't even know how it works, unfortunately, which I'll talk about later on. So it helps us to come up with a function, because if we can see something, we're likely to trust it. And this is, for instance, we say, okay, we would develop an ANN, we would train an ANN, then perhaps we can come up with a surrogate model that would explain to us how the ANN works. And once you have a surrogate model, or like a way that you can represent this ANN, then you become a little bit more comfortable, because you can see, okay, this input here, let's say F prime C, or compressive strength of concrete, is tied to reinforcement ratio by this amount or by this much, or this is why the algorithm came up with this prediction. This is what it saw. This is the relationship it linked it up to the output of our problem. Now we can see, we likely to believe. And once you have an expression, then you don't really have to use the algorithm anymore, because you use it once, you come up with the thing that you really need, the equation, the function, the mapping function. You don't have to rerun the model like many, many times. So now you're even cutting more time, because you're saving a lot of time. You don't have to, like for instance, in FE, you have to run the FE model every time. An experiment, you have to do an experiment every time to test a new parameter or a new variable. If you have a mapping function that can link the many variables, then perhaps you don't really have to rerun the algorithm at all. You can have it into an Excel sheet, or a hand calculation. The ones we have done, it can calculate 50 elements per minute. So if you think about that, usually an element in FE simulation, or like a member, structure member, takes 7-8 hours to 4 days of analysis. Now you can do 50 in a minute. So imagine how fast you could design a structure just by using AI. We don't really have to couple. If you do fire analysis, you have to do the thermal analysis first and take the thermal effects tied to the mechanical analysis or the structural analysis, and then see the impact of temperature on the element behavior as well as properties. In AI, it already knows the physics. We don't really have to reteach everything. We don't have to have coupling. You're cutting the time too. You're making it easier for you. And we don't have to worry about some input parameters, because if you teach AI the beam deflects because of the relationship between these parameters, then perhaps you don't have to use many parameters. You don't have to say, I need, like, for instance, this property at this temperature or that property at this temperature, because I'm interested in the aftermath of the problem, deflections, temperatures. I'm not really interested in what happens in between, because even if you think about it, if you run an FE simulation, you don't really go back into the FE model and start to see all these PDEs and matrices and break them down. You don't. You just look at the stresses at the end, the strains at the end. When you do an experiment, you then ask yourself, well, why did concrete crack there? You know concrete cracks at load, so you're only interested in the aftermath of the problem. Same thing, we can apply the same thing we always apply to AI, but we just have to be a little bit creative and we have to be more responsible when we do that. We can't just be blindly saying, I'm going to go for this, I'm going to go for that. So I have a very small problem here. I'm trying to figure out deformations in beams and temperatures in beams under different fire conditions. So what I do is collect some data, collect some parameters. My output would be the temperature at time so-and-so, deformation at time so-and-so. So I need AI to understand the relationship between these inputs or between these parameters to the output. Now, the question would always be, well, why did you pick these parameters, for instance? Or what about other parameters? Well, this is perhaps a discussion for a different day, but the goal is you pick these parameters because you spoke to an expert, because you know the physics of the problem, because you have done tests yourself. So you know the most important parameters. Is there a small chance that you might have missed a parameter? Yes. This is why I said you have to think of AI to use it responsibly. You have to have like an ethical component. We have to have like an engineering component, a science component. We can't just pick and choose 3 parameters or 4 parameters and assume everything is going to be fine. No, I'm just in this presentation, I'm trying to simplify the problem a little bit because I feel it's more of an introductory presentation. And then perhaps from there, if we can delve into more details later on. The goal I'm trying to emphasize is always think of baby steps. Think of your model as baby steps. So once you do that, you do your model, you have your prediction, you can see your fitness here. For instance, in my case, I said, okay, well, if the model prediction or the average error is 25 degrees centigrade, this is good to me. I'm fine with that. If the average prediction is 5 mm, I'm comfortable with that. And you can see we can also figure out deformations and temperatures in different elements very, very easily. So if you apply this equation here, you can find the deformation without having to do a test, without having to do an FE simulation. This is the beauty of teaching AI how to learn stuff. And now, instead of having predictions like black box, we have a mapping function that can tell us, for instance, okay, the relationship between concrete cover temperature exposure is this much. We can see the relationship between the parameters. So we are a little bit comfortable with learning that. Now, that doesn't mean that these are the only equations that somebody can come up with. There is many, many other variations to these equations. It makes sense to make the equations, that look nicely, easy to use, so people also can figure out what they do. And this is the beauty of an equation. Now you don't really have to use software anymore. All what you have to have is an Excel sheet. This is, for instance, the temperature rise we got from a test. You have your mapping function inputted, you scroll down, you have your prediction. And you can see that your predictions matches nicely with the experiment. Red is AI, black is experiment. If you have an FE simulation, it would also be very close. You can also do the same thing for deformation. You have the input parameters, you have your mapping function as an Excel, you just drag it. Now you have deformation of this element without having to hassle with how many elements, element types, meshing, experimentations, all those things together. It becomes much, much easier. And the beauty is, by now, hopefully everybody knows how to use an Excel sheet. So they don't really have to relearn AI or see what AI is doing. Because if you think about FE, not everybody knows FE, but everybody trusts FE's result. It's the same concept. It's just we're trying to be a little bit more proactive. You can also think of it, you say, okay, well, maybe I don't need to go and find an expression. Maybe I'm comfortable enough to having like a black box tool that I would like to use. This would be. So what we did in this case, we have some tests. This is with my colleague in Australia, Professor Thar. We have steel columns filled with concrete, circular as well as rectangular. And we did tests, we see how they failed. We did finite element simulations, parametric studies, several of them, and tested many parameters. And this is our phenomenon. Our phenomena is, as you can see, it's a little bit complex because it says, I need to find the ultimate strength of rectangular and circular, concrete filled cold formed steel, tubular columns, and they're concentric and eccentric. So the phenomenon is not just find temperature or find deformation. No, you have to find the ultimate strength. So now this is a much more complex problem. So now if you think about it, when you have a complex problem, if you would do this by hand, it's lengthy. It's lengthy. If you go to, like, for instance, AIRISE code or the Indian code, you have a procedure you have to follow. It always works. FE simulation, very complex, but it works. Can we simplify this problem? And you can actually do. If you have, for instance, a black box neural network or even some expressions, a mapping function, you can see that you have very good prediction capabilities. If you compare the prediction capability of the ANN to different codes, for instance, the American code, European code, Australian code, you can also see good performance. And even in this instance, for instance, some codes, they are extremely unconservative. You can look at this side. You can look at this side here. You can look at this side. However, AI's predictions are a little bit more conscious. They're a little bit more refined, which shows you the importance or the good stuff about using data, this data-driven analysis, but we can't just trust stuff like this. We have to be a little bit more careful because sometimes even if you have like perfect predictions, that doesn't really imply that the model understands what it's doing. This is why you always apply AI responsibly. You have to think of AI as a tool that helps you to see some things or some new stuff because we know how to design, we know the equations in code. But what does AI give us? It should give us something new so we can make our life better. We can see new stuff. This is a very complex problem here. You can see spalling is a complex problem in concrete beams, or concrete structures. So this is a column before testing. This is a column just by applying temperatures. You can see that you lost the cover. You can see reinforcement. The cross section is smaller, and you can see here like how does concrete spall? It explodes. And if you think of a firefighter in a building trying to put down the fire, if this thing explodes and it hits their oxygen tank, you can have now a blast. It's going to be very, very dangerous. So it's dangerous for the structure, for occupants, as well as for firefighters. So to predict spalling or fire-induced spalling, it's extremely complex because you have the material that's a composite material, concrete. You have water, cement, aggregate, fly ash. You have different components. You have shear reinforcement. You have water that needs to evaporate pressure. You have all these things together that interact at the same time at different temperatures because remember, fire starts small, then it grows. So it's a very, very complex mix of behaviors. You have a chemical component, you have a physical component, you have a material component, and you have a structural component because you have loads and boundary conditions. So how can we solve this problem? Go to the literature. Many, many studies, a lot of studies, very good studies. And this is my advisor, Professor Kudur here, one of his great examples of how we can derive expressions, derive partial differential equations that can help us solve this problem. And as you can see, it's not easy to solve. A lot of expressions, a lot of matrices and partial differential equations. So if this was to be in an industrial office or office of practice, it will be a little bit, maybe hard to solve all these things. This is more research oriented. So how can we fill the gap? How can we use AI to simplify this problem? Or can we even do that? The good answer is yes, we could. And what we did here, we actually developed an app that's based on a deep learning algorithm that says, okay, this is the app. It has a nice interface, so you don't have to worry about equations. You don't have to worry about derivations. You plug in your inputs, as you would see here, for a specific column, for a specific structure. And all what you have to do is scroll down and see the predictions. For instance, in this case, you would see that, you know what, this column or this structure is likely to have spalling. Now, the spalling could be minor or could be major. So in a way, AI tells you that I know there's going to be spalling, but I'm not really sure how much is it going to be. None of the existing methods can tell you this. It can tell you yes or no. It doesn't quantify spawning, but now we have a way that we can do that, and hopefully we will improve on that. And this app is free, so we're not even trying to make any money out of it. We just want the community to use it and test it and give us feedback so we can use and see how we can improve this, how we can make this life easier for us. The other example is, this is one of my favorite examples because now you would see stuff that are a little bit more outside of civil engineering, computer vision. So a question would see, well, why do you have this slide here in a presentation for civil engineering, right? Because think of it this way, computer vision is basically a technique that allows computers to understand content of digital images or videos. For instance, this is how a Tesla sees people, sees other cars, sees intersections. But if you could use this same algorithm, how can we apply it to us? Now watch this. You do this whenever you buy a new phone. This is how you teach your phone, well, this is my face. If you see me, please unlock my phone. Somebody in, I think, a research group in Europe, they had a research study that says, okay, well, if you have Mona Lisa, how would it talk if she was a human? So they applied this computer vision and saw, okay, if this is Mona Lisa from one picture, this is how Mona Lisa would talk, this is how it's smile, this is how she would communicate with you if she was to be alive. All these techniques are not civil engineering, but we can use the same algorithms and apply it to civil engineering. How can we do that? The following, remember spawning. Spawning is a complex phenomenon, right? Imagine this, there is a building, concrete building went under fire. After the fire, everything is fine, people escape, fire is gone. Your job as a civil engineer or as a structural engineer is to go back and see if the structure can be successfully opened for occupants. Well, what do? You go inside the building and you start to measure, okay, this is cracking here, deformations there, this is how much damage do we have, and then you come up with an assessment at the end of the day. So one, you have to be there physically. Two, you have to do an assessment. Three, God forbid, what if the structure is not stable after the fire, like after 2-3 weeks of fire, what if something happens? It would be dangerous. So wouldn't it be easier to run maybe like a, I don't know, like a drone, take some pictures and then ask whether AI to analyze the pictures for us or ask other humans to analyze it for us? In this instance, what we did is we taught AI, if you see this, this is going to be spawning, this is bad, and you can quantify the spawning. You can quantify your confidence. So you can see our algorithm told us the following. This instance here, this region, this is mild, and I have 72% that there is mild spawning. There is almost nothing there. If you look at the blue spawning, this is major spawning because you can see reinforcement. This is my confidence level, almost 96%. In this instance, you can see a lot of distortion. You can see there is cracks. This is 88%. I'm confident that there's going to be minor spawning. Now, if you have this, imagine the following. You can quantify magnitude of damage. You can estimate residual capacity. You can almost do it human-free. So you don't have to put anybody in danger. You can do it very, very quickly, very cost-effective, and safely. So you're getting the best of your world. Imagine this, if you have a structure, people have to relocate. If you do this very quickly, they're likely to come back home or make good decisions. This structure is bad, we have to put it down. We can't open it for public. Now you're making decisions. Decisions comes with confidence, reliability. You have to know how the algorithm works. This is the main picture. You have to apply AI responsibly. Now, in this instance, you can compare this prediction by major spawning and ask like a professor or ask an expert engineer, do you think this is really major spawning? Do you think this is minor spawning or mild spawning? Then yes. In this instance, you can see that our algorithm also mismatched. It said that this point has major spawning. I'm guessing that it meant this region here. But this shows you a very important lesson. Do not trust everything right away. Always question why an algorithm works and make the best out of it. So pause. At the end of the day, we're engineers. We trust things that we can see, that we can understand. We trust things that we can understand. So we really want to see, why does AI works really well? In the case studies I showed, it almost always perform better than traditional method, than coded provisions, than expert engineers. Here's the answer. If you go back and dig into the literature, you see many studies. For instance, this is from MIT. The dark secret at the heart of AI is no one really knows how the most advanced algorithms do what they do. They complemented this with a statement saying this could be a problem in my intuition. This is a problem. We have to understand how things work because we understand how experiments work. We understand how FE simulation works. We understand how codes work. So we can't use tools that we don't understand how they work. This is not the only study. Other studies at the Atlantic, this is like a very famous article. Not even the people who write algorithm really know how they work. Now, this could be like a very general statement, but there is a lot of things about algorithm that we don't really know how they work. So there is also one thing for us to think about. New York Times, artificial intelligence black box is nothing to fear. In their eyes, black box is good. You can read the article, or in some instances, it's good. We can always debate this. In my mind, engineers, scientists, we really need to understand things. We can't just apply them. Why machine learning is so hard to explain? It is a thing we used to explain. So we have to be able to explain decisions, to explain how AI works. Because if you can make them explain, then stakeholders, civil engineers, owners, governments, building officials can then understand and allow you to use AI, because without them being participant in this, we can't really use AI in practice. So all these things are questions that we have to answer. Think, how do we use AI in civil engineering? So we did like, I think my students surveyed 3,000 papers on AI, and then we refined them into 1,500 papers. And once you break things down, you would see that most of the algorithms we use are, the following, which you would see here. We collected the top 10 algorithms used by civil engineers. So the top 10 algorithms are actually neural networks, almost 30%, genetic algorithms, 26, 27%. And then you have the other ones, decision trees, random forest, PCAs, convolution networks, support vector machines, genetic programming, all these things. So this shows us something very, very interesting. This tells us like a community response to AI. We like to use neural network because we've seen the most success out of him. Most recent algorithm, for instance, XGB boost, random forest, PCAs, CNNs is new, relatively new. We didn't use them that much because we don't understand it, but AI neural networks has been with us for so long that now we're much more comfortable using them. But how do they apply them? This is how they apply them. Most of the time, if you read literature papers or review papers or research paper on AI in civil engineering, they would say this: well, we collected a database. We're gonna take 70% of the database as training data, 30% as testing data. 85% of papers you go with split. 5% of papers go with more recent advancements in data quality, data training, which shows you that we are extremely lagging. We like to use AI, or we started to use AI, but we are still lagging, which makes a lot of sense because things needs a little bit time to grow. But we could make it faster by understanding and teaching AI, because the future is going to be AI. We have to use it. FE's experiments will always be with us. It's only natural to use AI because if you think of it, like NASA, SpaceX, they can land space stations with AI. So if they can do that and find different planets with AI, don't you think that we can also apply it to civil engineering? Of course we can. The other thing is, okay, what fitness metrics do we use? And this is going to be a problem because it seems that we have a uniform distribution of metrics. Some people like R-square, RMSEs, MAPs. We don't really have a way of figuring out which and why. All of this tells us that our effort in civil engineering, at least at this point in time, it's positive. We're going towards that, but we don't have a standardized way of applying AI. People they go with their gut feeling, they go with their experimentation, which is good. This is how you grow a field. But at the same time, it could be dangerous because later on it will be very, very hard to justify decisions. So it's always easier to start early, teach new students how to do things early. The other thing is we did the following. For instance, as you saw here, we have 10 algorithms. Some of them are complex, some of them are simple. But in our problems, do we really need complex models? So we did like a very nice test. We applied, I think, 10 or 12 algorithms on the same problem. And this is what we found. If you compare the accuracy of the problems, so this is 98%, this is 100. You can see that all algorithms are they do a very good job. Almost all of them above 98%. Testing, validation, except for one here, but all of them are within 98% to 100% performance. If you look at AUC, this is a different metrics area under the curve. Almost all of them, 99.9 something to 1, they work really well. If you look at the logarithmic error, almost all of them are less than 0.05%. Very, very small. Very, very small. So this tells us something very important. If you go with a simple model or a complex model, you're very likely to solve the problem that you're trying to do, as long as we are within certain number of data points, certain limitations for our civil engineering problems. So is there really a need to go and apply very extremely complex models? If you think of it, perhaps not, because even when we do our analysis or design, we don't use the most complicated solution or procedure. We use things that we can see, that can help us analyze, that can make sense to us. So there is really no need to delve into, perhaps, let me add perhaps, there is perhaps no need into trying to understand or apply very, very complex model. Learn baby steps. Start with a simple model, then go to more complicated one if you need to. The AI's job is to make your life easy, not hard. Some of the other complex questions that we have to ask ourselves as a community, as researchers, whether civil engineers or scientists, what do we need from an AI tool? What does it have to have so we are comfortable with using it? When I think of this, I would like to see a tool that's not a black box. I would like to know how the algorithm works and how it ties each input specifically. This is how I can make confidence. I would like for the model to be explainable or interpretable. I want to see how it works, why it needs this much data. Do we need more data or less data? I would like to see something in the effect of cause and effect. I don't want just to have a prediction. I don't want to say if you have these input parameters, you're going to get this much capacity or this much response. I want to see because of this, I have this. I want to see causality. This is why one of my main research areas now is all about causality. I want to see cause and effect. I just don't want to predict the stuff anymore without knowing why. Well, I have a very nice figure here that says I blame the algorithm because if it doesn't work, you can't justify yourself. And worse, if it works, you can't justify yourself either. The most important thing from a scientist point of view or from even a practitioner point of view is new knowledge. We need to use tools to give us new knowledge and new insights into phenomena that we can see, that we can learn, we can deduce, infer, abduct new conclusion. This would help us improve as a society together, not just civil engineers, everybody together. You have to be confident. Remember, CE or civil engineering is all about people. We build the structures. People live in these structures. So if something happens, you're losing a lot of lives, which we cannot, agree to that. So we have to always be very confident. We have to be very reliable. This is why I always say use AI responsibly. You can't just use and apply it as is. Your decisions would affect other people's life. For instance, this is a nice example here of a pyramid. You can see that one small item goes down, everything falls into pieces. So you have to be careful not to be that one piece that is going to make everything else collapses. Don't complicate things. Start, simple. There is genius in simplicity. You don't really have to come up with the most complex model to solve a problem. You have to understand how things work out. Now, the question I always delve with, I always have a lot of discussion with, is the following. Do we need to apply AI or do we need to develop AI? What are the differences? What are the pros and cons? Most of the time, papers now, research, industry, they apply AI. We wait until our computer scientist colleagues develop something new and we take it and we apply it. Is it enough? Do we have to develop our own tools? Maybe that's a question for all of you. Think about it. How can AI supplement or complement testing, simulation, analytical method, theoretical derivation? Do we have to start to teach AI in our curriculum? Do we have to put like a civil engineering spin on it? Or do we have to teach it as a language, programming, for instance? These are questions that also need to be answered. The other question is, do we really need AI? For instance, like we know how to design structures. We know how to design concrete, steel, members, elements. We have years and years of experience. We have codes that tell us how to do that. Do we really need AI? Well, you can ask the same question, do we really need FE simulation, right? We need them because it's a new tool that would make our life easier, that give us attractive solution that traditional methods do not give us now. This is one way that we can need that can justify AI. It makes our life easy. Look at the economy. The slide I started with. Agriculture, manufacturing, mining, overall economy has improved with automation. It's very likely that civil engineering will also improve with automation. We just have to try how to. So after all these discussions, where we go from here. As you can see, AIs are algorithms. Algorithms are rules applied to data points to see patterns. So we really need quality and good number of inputs or observations. We have to have that, otherwise AI will be useless. We can just apply this. We also need to verify AI, verify our tools, be responsible. We have to be confident. We have to have some support. We have to have both industry and academia. They need to sit together because building codes are made with both. So we have to see, okay, do we really need AI? How can we do it? How can we use it? Because in 10, 15 years from now, the engineers we have, the students we have in our classrooms would be practitioners. So can you see the line? Can you see that? Look at mechanical engineering, look at electrical engineering, computer science, everything has been using AI. It's going to be our time very soon. The future is going to be, we have to use AI. So we need support. We need to understand how we can tie things together to help us all come up with. And as you can see, if you go to the internet or Twitter or Google, there's a hashtag, the future is AI, because it's very likely that a lot of decisions are made with AI. Now you go to a bank to get a loan, they give you an algorithm decision. They say the algorithm says, this much, approved or not approved, right? It's always going to be that we have to justify our decisions. So one of the take-home messages, we really have to talk. We have to talk to computer scientists, to other engineers, to see what can we do to have an interdisciplinary approach to AI. Not just in civil engineering, in all engineering. We have to ask, what do we need? How can we do it? Who can help us get there? It's a cycle of questions. Always ask yourself. We need to have databases. We have to share algorithms. We have to make things accessible and free. You can now go to YouTube. I mean, I learned everything from YouTube because all that, videos teach you tutorials how to run algorithms and stuff. Anybody can do that nowadays. It's not, you don't really, have to be traditional. It opens up stuff. We have to do tests. Always test your algorithm multiple times. Make sure it works. Make sure it's explainable. Make sure it's confident. All these things that we need to learn. We need to test to be able to apply AI, just like how FE started. Many testing before a software is even released to the public. That's the same thing we need to do. Again, I have to emphasize industry and academia. Everybody needs to work together. This is how we can make things happen. Because without that, it's going to be extremely hard for us to move forward, right? And I know we have students, so if you are undergrad or grad student, always ask yourself, why things are done this way? What can I do to improve it? There's a lot of opportunities for grad school, for practitioners to learn AI, to use it in their field. So it's a very hot area now. Perhaps you'll always see some brilliant students that want to push the envelope further than what we would do as professors or as academician or industry support. I remember when I applied to grad school, I was like, I didn't, I wasn't thinking about AI at all. But then from then you learn something new, it catches your eyes, you try to practice it, and now you get to do certain things. I hope one day perhaps this presentation might be helpful to some of you to see where we can go from here, how we can advance our knowledge from there. And at the end of my presentation, I know that there is a lot of brilliant minds out there. And if you happen to do anything with AI in civil engineering, I have a book that's going to be published by CRC, Thar and France, I think in early 2022. So if you have a study that you would like to publish, you can send it to me as a book chapter. You'll have it on the DOI. It's going to be freely accessible. You won't have to pay anything. And this book is titled Leveraging Artificial Intelligence in Engineering Management and Safety of Infrastructure. This is a book that I would like to have. I mean, so far, I think we have 14, 15 chapters from different parts of the world. I think I have one chapter from India. It would be really great if I can have another chapter from there, because I'm trying to highlight different countries, and I know that India is it's a almost subcontinent. So if you have any studies that you would like to highlight, please, share them with me. The book is going to be in print as well as ebook, so it would be interesting to have. We just finished a session on AI and concrete in ACI. Actually, they were very kind to me to allow me to have a session as well as a guest editorial where we have, I think, 14 papers from around the world on concrete and AI, believe it or not. It's amazing to see how the community comes together to work together towards something this big very, very soon. So these are some of the things I would like to keep in mind. There is a lot of opportunities out there to go there and explore, make yourself knowledgeable of those things. And of course, I always would like to thank my students for their hard work and effort. I wouldn't go anywhere without them. I would like to thank IITJ leadership, and I have a typo here. I apologize for that. Leadership, of course, my friend Dr. Ravi for his support, for his invitation, as well as the staff that helped us with coming up with this presentation. Again, apologies for my typo, and hopefully it will be something funny to remember this presentation with. At the end of my talk, I would like to thank you all for your kind presence as well as for your kind thoughts, and I wish perhaps we could do great things together in the future. Thank you very much.
Thank you, Professor Naser. It's a nice talk depicting various spheres of AI applications in civil engineering. And here at IIT Jodhpur, we do have significant emphasis of AI in our civil engineering curriculum. It's the time for question and answers. First, I would like to give over to Professor Shantanu Chaudhary, who is the director of IIT Jodhpur. Professor Chaudhary, do you have any questions?
So let me make some comments. Because I'm not a civil engineer, so I would hardly will have questions related to these. Although I work in the area of some of the areas of AI that you had talked here, and what we had also, as you have mentioned, that is there is a requirement and possibilities of civil engineers working with AI engineers and AI specialists and AI researchers together, and for next generation civil engineering systems. And there are lots of open problems which has been which can be addressed. And there are also limitations of AI. And if you look at today, when we talk in terms of explainable AI, dependable AI, verifiable AI, so those are actually possibilities needed for when we are looking at applications in civil engineering, other engineering hardcore systems. Computer science in that way always works in very safe zone. But the moment you come out of computer science and go into real engineering space, it has to be much more robust. And all this robustness in terms of algorithmics and other things are now coming into the AI space. And with reference to engineering domain, it is really becoming very, very exciting. In fact, this talk is being organized by School of AI and Data Science. And there, our whole focus is to actually build this kind of interdisciplinary groups and interdisciplinary research of AI fundamentals, at the same time AI applications. In fact, Ravi is trying to come up with a proposal of a center of excellence in intelligent infrastructure, where all these AI related problems and AI and infrastructure linked will be looked at, and we are hoping that would become a useful and center in the country, and we look forward to your help, your support, your contribution in that whole initiative. These are just general comments. I have just one question. See, you had talked about use of computer vision in terms of looking at the severity of fire and the temperature measurements. Now, the only question I have is that in terms of sensor characteristics, that there's a change in the color response and with reference to the heat from imaging devices to another device. And that makes, in many cases, AI-based algorithms may fail and lead to failures. So what kind of spatial precautions you had taken, or there was a standardization in terms of sensor characteristics that you had implemented? Because in many cases, there are also drifts in the sensor in terms of various environmental conditions into account. So what kind of steps you had taken in an algorithm to address these issues?
100%, 100%. And this is actually one of the reasons I only looked at the structures after the fire, once everything has cooled down. And I only looked at the damage. I didn't look at the damage during the fire because, as you mentioned, it's very hard. It would cause algorithm to go nuts. So what we did is we collected images for structures after the fire has gone, just to figure out the damage, so we didn't have to deal with the damage within the fire duration. Other than that, it would be very, very hard to collect data or to collect ground truth data points that would help the algorithm see, because you can't measure it. If you can't measure it during the fire, then you can't take a good picture of it, then the algorithm can't learn from reliable data. This would be a very good question for a future work for sure.
Thank you. And again, thanks for your time and for talking to us. And I personally hope that you'll have the chance to come to Jodhpur and spend some time with us.
I hope so too. That'll be a pleasure. Thank
It's
you
an
very
open
much.
invitation from our side.
Brilliant. Thank you. I would love to.
Thank you, Professor Chaudhary. Now I invite Dr. Toteja for the interaction.
Any other questions? Nobody has any questions?
I have no questions.
Maybe others like Professor Bhattacharya, Professor Datta, Ranju.
I do have a question actually.
Yeah.
You see, initially you talked about things like surrogate model, mapping functions, and all that. Now this is quite different than the technological side of it, like what Professor Chaudhary was just saying. Intelligent systems, right? Now these are two different facets, or they are linked somehow, because there are both types of problems are there in civil engineering today.
Right. No, at least in my eyes, I believe that if your phenomenon can be simplified into a set of data points, for instance, a tabular data points, then you could easily use a mapping function. If the problem is more visually or visual wise, you have to have data, images and videos, you would have to use a different type of algorithm, which would be like, for instance, computer vision algorithms, because I feel that would fit nicely there, because the data that you're using are images, so you need like a tool that can understand the image component. Other algorithm that you apply to tabular data, they may not be applicable to images or videos.
What I was trying to say is, you see, mapping function or surrogate model.
Yes.
Now we have really complex problems which we have not solved in civil engineering, like structural fire protection. You have basically the heat transfer, nonlinear heat transfer, and then nonlinear structural behavior, because properties will keep on changing. Now, when you deal with that, for example, we work sometime in things like, say, in of structure in sea, in splash zone, ingress of chloride, right, which initiates corrosion and things like that. Now, it involves a system of differential equations. The physics is complex because diffusion, advection, all this kind of thing comes into. And we have not really looked into this. Till date, it is all empirical or that kind of thing, or very simplified. The moment you try to go to the physics system of differential equation, even cloud computing takes a hell of a lot of time. So every day you will not do cloud computing. Perhaps you do cloud computing for a set of experiment design, and then possibly create a mapping function or surrogate model, and somebody can use it. Now, where does the artificial intelligence comes in there? This is one question. Other kind of thing that I was talking about, for example, 3D printing of concrete today. Right? The buildings, at least 2-story buildings people have made from 3D printed concrete, and it's a possibility. Besides infrastructure, there are many. So the first one I'm talking of, how does the artificial intelligence link to this? What I'm trying to understand is it's basically generating a kind of multivariate regression or ANN or surrogate model. Anything beyond that, that's what I said. There are many problems like this. There are many problems in civil engineering. See, we are using mechanics of 200 years old.
Yes.
But when you come to a large system, robustness of computation today is available through various ways.
Correct.
Right? In 1960s or 70s, we were doing by hand calculation what is called moment distribution. So
100%.
dynamics couldn't have been used. It was
Yes.
very difficult to use it, structural dynamics. But then computation gave us the facility. Why does artificial intelligence stands this kind of scenario? Because there are many civil engineering problems, which
100%.
yeah, when you try to bring in, when you try to bring in the physics, you have real problem. Like even building physics, you have acoustics, air lighting, fire, all that. Supposing I am to design an envelope for all that. So
Yes.
where does AI comes into that? How does it help? Maybe some of my colleagues, younger colleagues, might get research ideas from this kind of situations.
Exactly. 100%, sir. 100%. I agree with everything you mentioned. So let's say if you have a complex system like the one you mentioned with corrosion, you know beforehand the type of inputs that affect the system, correct? And if you know the inputs that affect the system, so you know this side. This is the phenomenon. This is corrosion. You know the output, which is basically level of corrosion, maybe under certain conditions. What AI can do is they can take these inputs with the observations you have done in your test, or you can collect from from literature, and then it would build a surrogate model for you, so you can map these inputs to the output based on some kind of a data-driven analysis that doesn't rely on physics. So this could be one way. The other way is what you could do is you could basically go back to the algorithm itself, and you can constrain it by applying some loss function that represents the physics of the problem. For instance, you would say, so whenever you solve this prediction, this is what the prediction would be from an equation, and this is how you tie it together. This is how you make the loss or the differentiation within the algorithm satisfy BDEs or embedded BEDs within the system itself. You can also teach an algorithm to go there. So you could do it from a purely data-driven point of view, where you just collect observations and you try to tie them together based on data-driven analysis. Or you could maybe a little bit more improved by trying to apply some constraints of the model, because the surrogate could give you a number that's completely outside the range of physical realm. It could be like corrosion -2. It doesn't make any sense. So you could tie it with a say, okay, it can't be negative. It can't be 1,000. It has to be within the certain range. So at least now the algorithm has to work twice as hard to satisfy first the data-driven approach, as well as the physics component that you constrain to the model. And now I didn't say if, I'm saying when we successfully do that, now you have a surrogate model, as you mentioned, that's extremely quick. You didn't have to use the experiments. You didn't have to use cloud computing that much, because now anybody can use this algorithm or this tool. What's important also too is if you have a tool, you can easily publish it so people can test it and give you feedback. So you can now increase your database, do further analysis, further refinement, because even the algorithm we've done for the spawning, the interface, sometimes we get questions and comments, and it says, well, it showed me spawning doesn't work in this case, but in the experiment it did. So we have to see now maybe we have outliers that we have to worry about. Maybe the physics of the problem is not really captured by those inputs we collect. Maybe we have to add more inputs. Maybe we have to add, I don't know, fly ash. Maybe we have to add cement content. We have to add how much moisture content. And it's more of a trial and error process. And I agree with you. It's going to be very hard to answer the question like immediately from the first shot. But I think, as you mentioned, we need like new blood to come and always help us figure out how we can improve from 200-year-old mechanics into something hopefully that the future would be much more inclined to. Thank you.
I have one question, Dr. Naser.
Go ahead, sir.
In the spawning problem, often the interdependency of parameters is discussed. And let us say we want to use that interdependency in our day-to-day design. Can AI try to track certain kind of similitude between that parameters? Like permeability is a one parameter, damage is a parameter.
Yes, sir. It's a very good question. So what you would, The answer is most likely yes, we could. And the way we do it is because now after training the model or the algorithm, now you have a model because it used to be an algorithm. Once it works, it become a model. And this model, what you would do is once you're comfortable with its fitness or the way it performs, you could say, okay, I'm gonna only change moisture content from 0 to 5, and I'm going to see the predictions, or I'm going to try to plot the differences or the influence of changing the moisture content with the spawning phenomena. What we call this like a partial dependence plot, for instance. So it shows you the influence of one feature on the overall prediction of the model. What you could also do, you could use other tools. For instance, you could use something like Chabley method. What Chabley method does, it says, okay, I have these 5 inputs. And for this prediction, I'm going to give you the reasoning or the weights I used to get that prediction. So if it gives moisture content a high influence or a high percentage, then you know that this feature has a significant influence on the prediction. So you could track this one by one. Now the question becomes is, because both Shapley as well as just verifying the parameter by itself is not really physics induced, because we don't do this in physics. It's purely data driven. How does this complement your analysis? So this is the fine line where expertise, where we have to be upfront. We have to say, well, this is data driven, and this is why actually one of the messages of this presentation is we can't just rely on computer scientist tools, because they derive tool, as the professor mentioned, for general stuff. We have to have tools from our own people, from our own field, that we understand the importance of knowing this, that we've done tests, we know the influence there, and we have to come up with a tool that helps us, that helps our AI even achieve better performance, because it's not just based on data driven, it's now based on data driven plus physics that we see, the physics that we learn in our tests, in our books, in our simulations as well.
Thank you.
Thank you very much.
Thank you. Professor Datta, do you have any questions? Professor Neeraj, do you have any questions?
I really don't have any question as such, but I was somewhat intrigued when he said that, we have these experts who give us an opinion, and then we want to essentially replace experts with AI. Hopefully more reliable experts. Not every expert is equally reliable. It's amazing that how we are trying to do the same thing in biology. We are trying to replace medical personnel with the experts, and biological parameters are probably many multifold as compared to civil engineering. Pardon me if I'm wrong. I could be very wrong. And we just don't even know what are the inputs. We can always come out with something which will say we have a 90% prediction, but we have not reverse tested it on conditions which we have not tested on. So do you have similar situation in civil engineering applications also?
Yes, sir, we do. I mean, I agree 100%. We don't have as many parameters as one would find in biological sciences or even medicine, because they have different types of DNA, genomes, and stuff that's much more headache to deal with. But even in our problems, which are simpler, because maybe we're dealing with, let's say, 10 parameters. Do we really have to use all 10 of them? Maybe only 5 would work, or maybe like you only need 3. So you have to do some analysis to figure out that. One of the methods I personally use is the following. If I'm trying to figure out a model that gives me deflection of a beam, I would start by the equations that we know from mechanics. I would go to those equations and I would say, okay, these are the parameters on these equations. So I'm going to start with them. Then I might go and ask other professors. I would say, okay, well, we have mechanics equations, but these equations were derived based on certain assumptions that they have to be satisfied. Now, what are some of the things that we could see in the lab that other parameters might influence those deflections? So here's where experts, like for instance, my advisors would help, because they have seen much more than I have seen. What we could also do, the third option is, and this is sometimes would be helpful if you have like a very large database, like big data stuff, you could run something what we call feature analysis. So feature analysis, it looks at different features and it tries to assign weights. It would say, okay, out of the 50 features you have, if you with this output or with this phenomena you have in mind, from a data perspective, those 6 inputs are the highly related to that feature. Now, I said related, I didn't say correlated, because you could have linear correlation, nonlinear correlation, you could have association, different stuff. So the relation between inputs to the output could be minimized a little bit. One other thing which we could also do, and I believe they do this also in medicine, if I'm not mistaken, they would use a lot of feature engineering or feature analysis, feature engineering and feature design approaches. What they would do, they would apply algorithms that minimizes features based on data perspective. For instance, principal component analysis could work. Other ones would be something like outlier analysis. You could use some double forest algorithm just to minimize the number of features that you have. So you could do it from a physics point of view, or like from a knowledge based, or from a domain expertise point of view, as well as from a data point of view. But here's the thing, as you mentioned, you could always, and this is why we have to use AI responsibly, because the ethic component has to be there. We're scientists, we have to deliver something ethically that satisfies not just, as you mentioned, a metrics for a paper publication or for a software development. We have to make sure that it also satisfies our people, the society as well.
Thank you. Thank you.
Thank you, sir.
Thank you, Professor Neeraj. Professor Vadera, do you have any questions?
No, I don't have any question, but it's very interesting actually. Very interesting to see that, how these new technologies are now coming into the domain of civil engineering, and of course, Professor Neeraj talked about in bio and all those things. So this is really very interesting, and I think together with IIT and we can have Clemson University collaborations and see that how we can utilize these technologies in the Indian context also. Thank you, and it was really wonderful.
Thank you, sir. Thank you for your kind words.
Thank you, Professor Vadera. Professor Datta, do you have any questions? Okay, now we will go to the questions from the attendees. The first question is from Dr. Debanjan Guhara. How do you calculate the residual strength from the photographs of fire-induced spalling?
Oh, well, that's a loaded question. It's actually a paper, and we're working on this paper right now. What we did is the following. So actually, can I show one of my slides quickly?
Yes.
Ravi?
Yes.
Okay, perfect. Thank you. Because I believe it would be easier to visualize what we did. If we go back all the way to the spalling phenomenon, I believe it was somewhere here. Yes. So we have this one. Yeah, so you can see on the right-hand side, you have a column full size. The other side is reduced. So what spawning does, it degrades material properties as well as it degrades cross-section. So your column is now smaller. So the way to calculate the residual capacity is the following. You know the initial volume. You can ask computer vision to figure out the new volume. So you can come up with geometry. You know the degradation based on color changes, chemical color changes because of heat, which computer vision should be able to capture. Not very successfully so far, but hopefully in the future we'll be able to capture it much more successful. If you can capture the temperature caused degradation, so basically the maximum temperature the element has seen, and the new geometry, you can calculate your capacity, because now you have the two things that you can calculate capacity for. You have the geometry and the material properties. If prime C reduced, Fy reduced for steel, you have the new width and depth of the column, length of the column. You can calculate cross-sectional capacity as an axial capacity. You can calculate new buckling length. So you can come up with an estimated residual capacity that you could not do earlier. And this is what we actually do in the field. Engineers go, they measure, they calculate, but they do it manually. Now you could potentially do it much quicker, much faster, and maybe in the next few years much more accurately as well, just by looking at the image, which if you think about it, it's amazing, because instead of going to a field, measure and do stuff by hand, you can take a picture of it and do all the analysis. Now, some of the limitations, of course, image orientation, member orientation, the type of cracking, the type of temperatures. Our algorithm is still a little bit struggling on this front because it needs like much more refined analysis. But hopefully, next 2-3 years we will be able to do this much more easy. Very good
Thank you.
question. Very nice question.
The next question is from Amit Chandra. As you highlighted, the AI algorithm needs relevant data in this regards. Is there any initiative that you are aware of which is for the application of test data on structural fire engineering, such as isolated structural beams, columns, and frames?
I think the answer would be ask Dr. Rabi. Dr. Rabi is now doing an initiative on steel structures. So he's collecting a lot of data points for steel structures. I know my group is doing good data collection on timber as well as concrete structures. So these are on my website. You can go to my website, download databases from there and play with them. If you have databases, I would always encourage sharing the databases. And now there are websites like, for instance, Mendeley. You can upload your database. It will have its own DOI, so it can be cited. So it's good for citations, for publications. It's good for the community to go and test and build databases. But if you're asking for official initiatives, I don't think we do have any here in the US. I know NSF, National Science Foundation, is doing something for earthquake analysis, wind analysis, but not for fire. I hear that maybe in Europe something is going on, but I'm not 100% if it's publicly released yet or if they are going towards that direction. I hope this answers your question.
Thank you, Professor Naser. Since there are no other questions, now I invite Dr. Toteja to present the memento.
Thank you very much, Dr. Naser. It was indeed very interesting presentation.
Thank you, Marcel.
And I was very happy to see, the lot of publications you have.
Oh, thank you very much.
Yeah, in year 2021, I saw that around 12 or more than 12 publications you have this year. And in most of the publications, you are the first author, and also it is also in high impact journal. So it is really very, very, very appreciable, And as Professor Chaudhary told that you kindly visit Jodhpur, Rajasthan, whenever convenient to you.
I'm 100% confident I will.
Yeah. But till that, a small piece of token, this is made by our artisans, in Jodhpur. So on behalf of Jodhpur City Knowledge and Innovation Foundation, and also on behalf of IIT Jodhpur, I present you, kindly accept it and oblige. Thank you very much.
Thank you very much, sir. I appreciate all the support I got. It was amazing and interesting to be with this panel. It was eye-opening to see that. Hopefully one day I plan to visit my friends out there, and it will be an amazing day for sure.
Wonderful. Most welcome.
Thank you, sir.
Thank you, Dr.